Angle is defined as length of the arc divided by the radius. So as you look at that, you see that the angle between the angle theta shown there is the length of the arc AB divided by the radius. Now, what's the unit of AB? It's a length. Meter. What's the unit of radius? Unit of radius is also a length. It's meter. So what's the unit of angle? Nothing. See? Angle has no unit. But we can also call it radian. So if you don't write a unit with angle, it's okay. Or you can call it radians. Now 360 degrees is 2 pi radians, and that's the symbol for radians. 360 degrees is 2 pi radians. That's how we get the circumference of a circle as 2 pi r. Circumference of a circle is 2 pi r, isn't it? That's how you get it. Now you need to convert from one to the other. What's 30 degrees? 30 times 2 pi by 360. 30 times 2 pi by 360, that gives you pi by 6. What is 45 degrees? Do the same, 45 times 2 pi by 360. So to convert degree into radian, just multiply by 2 pi by 360, which is multiplying by pi by 180, isn't it? Because 2 pi radians is 360 degrees. So that's how you get it. 90 degrees is pi by 2, and so on and so forth. Is the angle described in 1 second? And that's how it's defined. The same figure again. The symbol is omega, and omega is theta over t. Theta is the angle, and t seconds is the time taken to finish that, to cover that angle. So what's the unit of angular velocity, Suleiman? Radians per second. Radians per second. It might be written as RAD per second, so it will be radians per second. That is the unit. There comes the unit. Radians per second. That's how it's written. Rad per second. That is angular velocity. Now I'm going to connect angular velocity with frequency. Acceleration is actually defined. Acceleration was the change in velocity by time, wasn't it? Same thing here. Change in angular velocity by time. And the symbol for angular acceleration is alpha. So whenever you see alpha, you should remember that is angular acceleration. It's d omega by dt. And obviously its unit is going to be radians per second squared, isn't it? Because it's radians per second divided by second. So it will be radians per second squared. That is angular acceleration. Straight line, I'm going to compare that with rotational motion and look at all the equations. Velocity is displacement by time, angular velocity is theta by time. The unit of velocity is meter per second, the unit of angular velocity is radians per second. Okay. You remember this equation? V is V naught plus AT. You have a corresponding equation. Omega is omega naught plus alpha t. You remember this equation? We called it the king of equations. Delta x is equal to V naught t plus 1/2 AT squared. All right, you have a corresponding equation, delta theta. So where you have delta x, you're going to have delta theta because it's angle. Omega naught t plus 1/2 alpha t squared. And remember this? V squared is V naught squared plus 2a times delta x. That's the corresponding equation. So you have a whole bunch of equations exactly similar to what we already did in translatory motion. Now I'm trying to connect linear velocity with angular velocity. That's what I'm trying to do. And it's a simple two-step derivation. Okay, what's that? Theta is AB by R, already defined. Angle is length of the arc divided by radius, isn't it? And so switch AB is R times theta, and velocity is defined as AB by T. Velocity is AB divided by T, of course that is. And substitute for AB as R theta, you get R theta by T, and theta by T is omega. So you got velocity is R omega. That's a very important equation. Worth writing one more time. That's the relation between linear and angular velocities. Tangential acceleration is dv by dt, that is d omega r by dt. R is the radius, is a constant taken out, so it's r d omega by dt, which is r alpha, understood. Radius is a constant, so that's why it's taken out, and that's how you get the next formula. That is the relation between tangential and angular acceleration. Isn't it almost the same, similar formula? Just multiply the radius with the angular, you get this. See, multiply the acceleration with the radius, you get this. It's a similar formula. We did talk about radial acceleration. It's also called centripetal acceleration. It's represented by AR, and the formula is V squared by R. But velocity can be written as omega times r from here. So square both sides, square velocity, you get omega squared r squared. One of the r's gets cancelled. So you can also write it as omega squared r. Radial acceleration can be written as omega squared r. Tan rule. To find the direction of omega. It's a vector. Angular velocity is a vector. Now, if you take a look at this figure, you know without me telling. Right-hand rule. Watch. If it's rotating this way, hold your fingers towards the tips in the direction of rotation, and the thumb gives you, isn't that what it's saying? Gives you the direction of angular velocity. So if it's rotating that way, angular velocity is up. But if it's rotating in the opposite direction, angular velocity is down. Can you make out that? That's all. So whenever you see anything rotating, the direction of angular velocity is along the axis, number one, and it could either be out of the plane or into the plane, depending on how it's rotating. So every time you'll have to use the right-hand rule. You see something rotating this way, okay, it's this way, isn't it? Okay, so the angular velocity is up. If it's rotating the other way, angular velocity is down. So angular velocity is always along the... Yeah, if you're speeding up, the angular acceleration has the same direction as angular velocity. But if you're slowing down, then angular acceleration has the opposite direction.
The moment of inertia, right?
That's the force applied, and there you see the torque. To calculate the torque, you multiply the distance with the perpendicular component of the force. You multiply the distance from the axis with the perpendicular component of the force. Okay, so tau is r times f perpendicular, which is rf sine theta. If you take a close look at that figure, you see that the blue arrow shows you the direction of force, isn't it? It can be broken up into f parallel and f perpendicular. Is that right? And when you calculate the torque, you only take the perpendicular component and multiply it with the distance. And torque can be written as r cross f. And do you know that a cross product gives you another vector? Have you done cross product? The cross product of two vectors will give you a third vector. And did you also know that the direction of whatever the cross product is will be perpendicular to the plane containing the other two? The same thing that I was talking about. There is a force applied at a distance r, and you know that the torque is force is mass times acceleration. We already saw that acceleration is r times alpha. Torque is F perpendicular times r. So just substitute mr alpha times r. That gives you mr squared alpha. Is A, can you write A as R alpha? Yes. And then just plug in torque is F perpendicular times R. So F is mass times A, so mr alpha times R, so mr squared alpha. Are you getting something close to this? Does that formula agree with this? Yes, it does. Except that in this place, what do you have? In the place here, you have what? mr squared. You can see m times r squared, isn't it? That's called I. I is the symbol for rotational inertia. So tau is I alpha. If you're talking about rigid object where there are so many particles close together, you can write the same formula as sigma 1 to n mr squared alpha, because you're taking the rotational inertia of every particle, adding them up. So you get this. I is called the rotational inertia. So when you take that summation, alpha is taken outside because it's a constant for all the particles, okay? And then you have sigma mr squared, which is called I. So you're adding up the rotational inertia of every particle. That's what I mean. So the sum of all the rotational inertias, that's I. So that's our final formula. So here is the comparison now. Net force in linear motion, net force is equal to mass times acceleration. And in rotational motion, net torque is I times alpha. So this is the equivalent of Newton's second law. You remember that F is equal to ma is Newton's second law. So in rotational motion, tau is equal to I alpha is the equivalent. And the unit, as I told you, the unit of moment of inertia, well, it's also called moment of inertia. Rotational inertia, moment of inertia. The unit is kilogram meter squared because of that formula. And surely I depends on the axis of rotation, where you rotate it.